Hello, my name is Magnus Petersen. This video is about a new method for doing portfolio optimization, which is extremely fast to compute as it only takes a few milliseconds for a portfolio of 1000 assets. It is fairly simple to describe and implement. It can handle both positive and negative portfolio weights, and it is extremely robust to estimation errors in the correlation matrix because it will only lower the portfolio weights. So the worst that can happen is that it moves too much of the portfolio into cash. Now, before we get into all that, I first want to briefly discuss politics. If you don't want to hear my words of wisdom on these matters, then there is a link below the video so you can skip to the main content. The reason I want to discuss politics is that the Western world is now almost entirely ruled by the political left. They set the overall political agenda and they control most of the news media, entertainment, academia, and big tech corporations. And increasingly over the last few years, the political left has assaulted anyone who disagrees with them. Political commentators on the right often assume that people on the left are acting in good faith, but I strongly disagree with that notion. From my experience growing up in Denmark, as well as from traveling around the world and often living with leftists in their homes, it is my clear impression that the fundamental driver for people on the political left is pure narcissism. But what exactly is the political left? It used to be about the redistribution of wealth and power in society under the pretense of wanting to give the working class a better life. But it has been a very long time since the left did anything to actually help the working class, and in recent decades, left-wing parties have increasingly been run by and for the elite. The left still needs the working class to vote for them, so the left-wing parties will pretend that they serve the working class, when in reality the left despises the working class. The main argument that leftists always make is that they are morally superior to everyone else. The former US President Barack Obama always said that he was on the right side of history, which is already a big warning flag that he is a narcissist. During the last election where the American left badly wanted to get rid of Donald Trump, they had two mantras they kept repeating. The first was that Trump put children in cages at the Mexican border, and the other was that Trump had said that neo-Nazis were very fine people. Both of these are lies that can easily be debunked by a few minutes of searching on the internet. It was actually Obama himself who started to detain migrant children because many of them were being trafficked by criminal cartels. So it was done to protect the children until the border guards could make sure the adults were their real parents. Obama stopped telling this lie about Trump after Joe Biden became president because the US border became flooded with migrants that Biden had promised to let into the United States, and the border guards then had to put far more children in cages than Trump ever did. The second lie is one that Obama still tells to this day, even after they won the presidential election, and the lie is that Trump had praised neo-Nazis in a speech. I encourage you to find the original video of Trump if you can, where you can see that Trump did the exact opposite. He strongly condemned neo-Nazis and racists, so it is incredibly brazen of Obama to keep repeating this lie when everyone can easily find out that he is lying. But the political left are masters of propaganda. One of their oldest tricks is to rebrand Nazism as a right-wing ideology, so anyone who is even mildly to the right must therefore be a potential Nazi who wants to put other people in gas chambers. But Nazi ideology is not conservative, it is not libertarian, it is not Judeo-Christian, nor is it anything else you could reasonably associate with the political right. Nazism is a left-wing ideology. It even says it in the name, because the word Nazi is a contraction of the German words Nationalsozialistische Deutsche Arbeiterpartei, which means National Socialist German Workers' Party. And if you read the original party program, it is a collectivist ideology where the state and its leaders have full control of the people under the pretense of being for the common good of everyone. And that is really the key to understand leftist ideology. It is all about power and control. Whether it is called socialism, communism, Nazism, or fascism, they are all left-wing ideologies that want to take people's wealth and freedom away to enrich and empower themselves. The milder forms of leftist ideology just have super high tax rates like in the Scandinavian countries where I come from. So the leftist leaders get to control what people spend their resources on. But this often develops into more and more tyrannical rules about everything else. Now let me give a few examples of the more sinister sides of the political left to show that they are in fact some of the most immoral, vile and narcissistic people on the planet, even though they always claim to be morally superior. I know this is going to sound like a crazy tinfoil hat conspiracy, but it's all true and you can check the facts yourself, although it will be a bit difficult if you don't speak Danish. The Danish foreign minister in the year 2021 is a pedophile rapist, by his own admission. Let me explain. In the year 2008, this man was 34 years old and he had sex with a 15-year-old girl, whom he was teaching and mentoring at a youth camp at the Social Democratic Party. It was a big story in the news that he had sex with the girl, but the Social Democratic Party assured everyone that the girl had consented and it was a romantic relationship, although the party admitted that it was perhaps inappropriate for an older man to have a sexual relationship with such a young girl. 12 years later, in the year 2020, during another round of cases about sexual harassment and abuse amongst left-wing politicians and leaders in Denmark, the case from 2008 resurfaced again, and this time it was revealed by witnesses to the event that there had in fact not been consent, that the 15-year-old girl was tricked and psychologically coerced into having sex with the 34-year-old man, and afterwards the girl was completely beside herself and crying profusely. It clearly was a rape, not by physical and violent force, but by emotional and psychological manipulation and coercion. The Danish law protects specifically against cases like this, where an adult is in some position of authority and power, such as being a mentor or a teacher to a person under the age of 18, in which case any sexual relation is illegal, regardless of whether there had been consent or not, and the police is required to raise criminal charges even without a formal complaint from the victim. Now, this man has admitted repeatedly in the news that the sexual intercourse took place, and the Danish law is then very clear, so he could be convicted immediately in a court of law, where he would receive up to 4 years in prison. But nothing has happened, and he is still the foreign minister of Denmark to this day. I suggest you look up who he is, so you can see what a pedophile rapist really looks like. It's not how they look in the movies. Instead, it's a smooth, well-dressed man with a big, confident smile. But the story is actually even more sinister, because the female leader of the Danish Social Democratic Party, who covered up the pedophile rape in 2008, she went on to become the first female Prime Minister of Denmark just a few years later. She is married to a British left-wing politician, who is the son of a very famous and very powerful left-wing politician from the UK, where they call their version of the Social Democratic Party for the Labour Party. And for several decades, the British Labour Party covered up Muslim paedophile rape gangs operating in the UK that were gang raping, pimping and prostituting tens of thousands of ethnic British girls down to only 12 years of age. Sometimes they even murdered the girls. One of the main people to inform the British public about this crime against humanity that the British Labour Party allowed to happen for several decades is a man who goes by the pseudonym of Tommy Robinson, who saw this happening to his own young cousin and wanted to warn the rest of the public about what was really going on. He ended up having more followers on social media than all the major British politicians and parties combined, and then one day, poof! He was completely gone and banned from all social media. The Facebook Council that decides on principal cases about who should be banned, including the ban of Tommy Robinson, as well as the ban of US President Donald Trump, that council consists of a number of people with links to the political left, including the first female Prime Minister of Denmark, who I just told you covered up a pedophile rape by one of her lieutenants in the Social Democratic Party, and who is married into one of the most famous and powerful left-wing political families in the UK, which helped cover up decades of pedophile rape gangs operating in the UK. But it gets even worse, because that woman, after she had been the first female Prime Minister of Denmark, and before she became a member of the Facebook Council, in between she became the leader of an organization called Save the Children. And just yesterday, I saw an ad on YouTube from this organization claiming that they are fighting against sexual abuse of children, yet the organization has been led by a woman who covered up sexual abuse of a child. Back in the year 2019, the Social Democratic Party in Denmark won the election again and got the second female prime minister in Danish history, which was a woman in her early 40s who promised to be the prime minister for the children. But then she selected the pedophile rapist that I just told you about to become the foreign minister, which he still is today. And there is now a very high risk that he could go on to become the future prime minister of Denmark. That's right, a pedophile rapist might become the future prime minister of Denmark. You might say that it is only the top of the political left that is corrupt, and normal left-wing voters are decent people who mean well and have the best intentions. But then explain to me why the Social Democratic Party is now having the highest voter approval in decades. Clearly, their voters have no problem with the sexual depravity of their leaders. The main question is, why are people on the political left so morally bankrupt? As I said in the beginning, it is simply because they are narcissists. They do not mean well. They exploit and plunder everyone they get into contact with, and then they have the nerve to say that they are the ones who are morally superior. If you go back to the 1970s, it was not uncommon for the political left in Denmark and other European countries to advocate for the legalization of pedophilia. For example, in France, a group of leading philosophers and intellectuals strongly advocated for this in the French media and public debate. One of those people was a man named Michel Foucault, who is one of the intellectual fathers of modern leftist ideology, such as critical theory and postmodernism, which is currently wreaking havoc, especially in the United States. In reality, Michel Foucault was a sadomasochistic pedophile who liked to rape little boys, and tried to get that legalized in France. His philosophical ideas were basically designed to make people question their own sanity and ability to reason logically, with the clear intent that people then wouldn't object to him raping their little boys. And that philosophical foundation, that you cannot trust your own ability to reason, is now one of the main ideologies of the modern political left. The reason that the political left has been able to conquer the entire Western world is because good and decent people haven't spoken up in time. This is because the main tactic of the left is not only to divide and conquer, but to brutally intimidate anyone who opposes them. And one of the main ways of doing this is to claim moral superiority. So if you oppose the political left, it naturally means that you are immoral and evil. But in reality, it is the political left that is immoral and evil, as I just gave a few examples of. Fortunately, it looks like the madness of the political left has reached a peak, and sanity is slowly returning to the Western world, as more and more ordinary people are objecting to the insanity and pure narcissism of the political left. Let's keep that momentum going and use every opportunity we can to oppose them. Now let us move on to the topic of portfolio optimization, where I first want to make a few critical remarks about academia. What you see here are slides from a university lecture at MIT, which is one of the world's elite technical universities. The lecture is a few years old, but it is the same material that universities are still teaching today, which is so-called Mean-Variance portfolio optimization that was invented in the 1950s by a young man named Harry Markowitz, and he was awarded a Nobel Prize for that work in 1990. The main idea is to try and maximize the portfolio's mean return while minimizing its variance, in the belief that variance is a good risk measure for investing. But as we will see in a moment, variance is actually a horrible risk measure for investing, and because of how the Markowitz method works, it can result in the portfolio getting concentrated in losing assets that are highly correlated, so it actually becomes a so-called double whammy of risk-taking instead of minimizing risk as it claims. These lecture slides are very mathematical. It is very typical in academia that professors like to make everything look very sophisticated and advanced because it makes them look incredibly smart. But often they forget to ask themselves, if their ideas make any sense in the real world. Professors often get completely detached from reality, so their work becomes more like so-called cargo cult science, which is something that is made to look like advanced science, but is really just a very crude imitation of science. In general, I think there are two main problems with academia. The first is that professors are usually employed for life. Even if they don't officially have tenure, it is still very rare that university professors or lecturers get fired. Most university professors never do any important work, and most of them never even try. But instead of giving up their position to let someone else try and solve some important problems in the world, most university professors just become drones for another 30 years until they formally retire. The paper I will present in this video probably took me 6 to 8 months to research and write, which is actually quite fast, but it is still 6 to 8 months of work that I paid for myself instead of having a job. And I have actually spent years upon years doing research like this, for which I have never been paid. I do this because I believe that some of my work is very original and very important. But it is extremely rare that people will sacrifice years upon years without being able to earn a living from their work, especially if they have the skills to make a good living somewhere else. So there are a lot of talented people who would like to do highly original research for the common good of the world, but who never get the opportunity because there are so few positions available in academia and they are already occupied by the professor drones. The second big problem with academia is that even if you do manage to make a tremendously important and original discovery on your own, your work will most likely not get acknowledged by academia anytime soon. Because the professor drones, who never have and never will do any important work themselves, they are either too narrow-minded so they cannot even see why your work is important, or they will simply not acknowledge that it is important because that would make themselves look incompetent, so they will just ignore major discoveries to maintain their own good jobs and high status in society. This has brought academia into very serious trouble because they now have so few people who are doing truly original and important work. I think that in 10 years, you will be able to get a much better and much cheaper education on the internet than most universities can offer. And I also think that in 20 years, the Chinese universities are going to be vastly superior at research than the Western universities, but then the Chinese dictator is probably going to decree that all of their best research will only be published in Chinese so they can keep it to themselves. If academia in the Western world does not undergo serious reform very soon, then it will be as good as dead in just a few decades. The key is to get rid of tenure and long-term employment, unless a person is a truly gifted scientist or teacher. But academia has been specifically constructed to protect mediocre professors, so they can have a good salary with lots of job freedom and a high status in society, and they are not going to give this up anytime soon, and that is why I am very pessimistic about the future of academia in the Western world. So now we get to the main content of the video, and this is the paper that I wrote. As I mentioned before, I think I spent somewhere between 6 and 8 months researching and writing it. I am not sure exactly how long because I first got the idea during the spring of the year 2020 when the financial markets crashed during the coronavirus panic, but I only actually started working on it in the beginning of the year 2021, and I sometimes had to work on other things as well, so I don't know exactly how long I spent on this, but probably somewhere between 6 and 8 months. Although the paper is more than 160 pages long, it mostly just consists of plots and analysis of the statistical results. As you will see in a moment, the new portfolio method and the diversification algorithm is actually quite simple. So the idea with this video is to give you an overview of the paper so you can more easily study all of the details by yourself. Here we have the table of contents of the paper, and it is roughly divided into 3 parts. The first few sections are about the mean-variance portfolio optimization method that was invented by Markowitz, and why that is wrong, because variance is a horrible risk measure for investing. And then a few sections debunk other common beliefs from academia. And then the second part is section 7 and 8, which presents the new portfolio method, which are called the filter and diversify method. And then the third part of the paper are a lot of tests on real-world data. I'm going to go through all of these sections, but some of them will be very quickly. And again, the idea is just to give you a quick overview of the paper, so it will be easier for you to study it in more detail. This section defines mathematically what the mean and the variance is and how it is calculated, and gives a few examples. And this is very important to understand because the mean-variance method by Markowitz tries to maximize the mean and minimize the variance. So it's important to understand what these actually are and what exactly they are measuring. And then the next section gives several counterexamples why the variance is a horrible risk measure for investing. The first counterexample is a comparison between two assets, A and B, and we show them in plots like this. So asset A is the blue curve and asset B is the yellow curve. These are so-called normal distributions, which are these smooth bell-shaped curves, but it could be any kind of probability distribution, because the problem is that variance is a horrible risk measure. It has nothing to do with the exact shape of the distribution. Let's say there's uncertainty about the return on each of these two assets. So the mean return of both assets is 10%, but the variance, or equivalently the standard deviation, is only 4% for the blue curve, while it is 8% for the yellow curve. So the standard deviation is twice as high for asset B as it is for asset A. But let's say that these are the actual probability distributions. So most likely we will have an outcome around 10% for both assets, but there's more uncertainty for asset B than there is for asset A. It is possible that we might have an extreme outcome, let's say minus 35% return on both investments, because this value here is not exactly zero. It is very close to zero, but not exactly zero. So it is possible, but it's highly unlikely. But let us say this is the actual return distribution. It is not an estimate. All of these counterexamples, let us say that these are the actual return distributions. They are not estimates that are calculated by some model that may be very wrong. These are the actual return distributions. And the first example here is the only case where you can say that the variance or standard deviation is a good risk measure. Because as the variance goes up, it is possible that we can have higher returns, but that also makes it possible that we can have much lower returns. So if you want the possibility of a higher return, let's say plus 30%, then you have to take asset B, but that also gives you a much higher probability that you can have losses compared to asset A. So this makes sense to say that the standard deviation or variance is a good risk measure in this case. Now let's look at the second case. Now asset A still has a mean return of 10%, but asset B has a mean return of 20%, and the standard deviations are the same. So for asset A, it's still 4%, and for asset B, it's 8%. In the title of the plot, we have written the probability that asset A has a lower return than asset B, and that is 0.87 or 87%. This assumes that the two asset returns are completely independent, but it shows that there's a very high probability that asset A will have a lower return than asset B, even though the standard deviation for asset A is only half that for asset B. So if the standard deviation or variance, I'm going to use these two terms interchangeably so I don't have to repeat myself all the time. They are equivalent because the variance is just a standard deviation taken to the square power. So asset A has half the standard deviation of asset B, and if the standard deviation measures risk, that would mean that asset A would have half the investment risk of asset B, but there's an 87% chance that asset A is going to underperform asset B. So it is absurd to say that asset A has a lower risk than asset B in that regard, because most of the time asset A will underperform asset B. And remember, we are assuming that these are the actual return distributions. These are not from some model that have made estimates that may be wrong. And clearly it makes no sense to say that the standard deviation measures risk here. And the third counterexample is where asset A now has a negative minus 10% mean return. And we see over here that this means that the probability of loss for asset A is 0.99. And asset B still has a mean return of plus 20% with a probability of loss of 0.01. The standard deviations are the same as before, so the yellow curve is wider with a standard deviation of 8%, and the blue curve is more narrow with a standard deviation of half that, only 4%. The title shows us that the probability that the return on asset A is lower than the return on asset B is 1.00. This is actually rounded up. It is 0.9997, something like that. Most of the time, asset A is going to underperform asset B, and most of the time, asset A is going to result in a loss because most of the probability distribution here is negative. But if you believe that the standard deviation measures investment risk, you would say that asset A has half the investment risk of asset B. Can you see that this is completely absurd? And it is baffling to me that after 70 years, the world's leading finance professors still haven't just drawn curves like this and see, you know what? It really doesn't make sense to use variance and standard deviation as a risk measure in investing. But to this day, the leading finance professors of the world are still using variance as a risk measure. It is moronic. I should say this, that I am humble enough to say maybe I have completely misunderstood what Markowitz meant. But so far, nobody has been able to give me an explanation of how this is supposed to measure risk. Okay, let's see some other kinds of counterexamples why the variance is not a good risk measure. And this has to do with the probability of loss as we change the variance. So in all of these plots, the mean return is the same, it is minus 10%, but we change the standard deviation. In the first plot on top, the standard deviation is 1.0%, and you can see that this gives a very narrow return distribution. And the probability of loss is 1.0. And again, this is rounded up, but this would be 0.99999999999999999999999999999, something like that. It is possible to get a positive return here, but it is extremely unlikely. So the next plot, we have the same mean return of minus 10%, but now the standard deviation is 5%. This means the return distribution gets a lot wider because that is what the standard deviation measures. It measures the width of the spread of the distribution. Now we see that the probability of loss is only 0.98 because a small part of the return distribution is now positive. It is more likely that we have a positive return than when the standard deviation was only 1%. And if we continue to the next plot here, where the mean is still minus 10%, but now the standard deviation is 10%, and even more of the return distribution becomes positive, so the probability of loss is now only 0.84. And in the final example, the standard deviation is now 20%, and the probability of loss is 0.69. Notice what happens here. As the standard deviation increases, the probability of loss goes down. Think about this for a second, because if you say that the standard deviation measures investment risk, but as the standard deviation increases dramatically, the probability of loss goes down. This doesn't make any sense. That's not how it's supposed to work. It is because the standard deviation measures the spread or width of the distribution, and more of that distribution becomes positive, so the probability of loss goes down. But if the standard deviation was a good risk measure, this should be the opposite. As the risk goes up, the probability of loss goes up. But the problem here is that when the mean return of the distribution is negative, it has the opposite effect. And this makes you think if finance professors for 70 years never have considered a return distribution with a negative mean. These are very simple counterexamples, and I came up with them fairly quickly when I studied Markowitz Mean-Variance portfolio optimization because it really puzzled me why they were using the variance or the standard deviation as a risk measure. If you come from an old school world of investing where you think about the prospects of the company, how much can it grow, what are the valuation ratios, and all of these things, when you have an old-fashioned way of thinking about investment risk, this doesn't make any sense. And it doesn't make any sense when you consider simple statistical counterexamples like this either. I don't know why finance professors for 70 years haven't done this. I don't know why they gave Markowitz a Nobel Prize for this. Let's go to the next plot, and this is probably what finance professors are thinking about. So now the mean is plus 10% for all of these cases, And we use the same standard deviations as in the previous plot. So here it is 1%, in the next plot it's 5%, then 10%, and in the plot further below it's 20%. And because the standard deviation is the spread of the distribution, when it is only 1%, it is very narrow around the mean. As the standard deviation gets bigger, the spread gets bigger, and already when the standard deviation is 5%, the probability of loss is now 0.02 because a part of the return distribution has now become negative here. And when the standard deviation is 10%, even more of the return distribution is negative, so now the probability of loss is 0.16. And when the standard deviation is 20%, the probability of loss is 0.31 because even more of the return distribution is negative. So here the standard deviation is a decent risk measure because when the standard deviation goes up, the probability of loss goes up and the magnitude of the possible losses are bigger. So here it makes sense, but when the mean return is negative, it doesn't make any sense. So those counterexamples were comparing the return distributions of individual assets against each other. What if we consider an entire portfolio of assets together? Well, let's consider something called the minimum risk portfolio. And this is where the variance or the standard deviation is at its lowest possible point. The top plot here shows two assets, A and B. And A has a mean return of minus 10%, and B has a mean return of plus 20%. And if we scroll down a little, we see that asset A has a standard deviation of 2%, and asset B has a standard deviation of 5%. Furthermore, the return on these two assets is negatively correlated with a coefficient of minus 0.5. So this means that if we make a portfolio where we combine these two assets, because they are negatively correlated, it will give a lower variance than either asset alone. And if we scroll back up, that is exactly what we see in this curve here. This is also called the Pareto or the efficient frontier of the portfolio. And it is simple enough to calculate when the portfolio only has two assets. It gets a lot more complicated when we have more assets than that. What it shows us is that the minimum variance is at this point here. And if you believe the variance measures risk, you call this the minimum risk portfolio. And it has these parameters. It has a mean return of minus 3.1%, and the standard deviation is 1.4%, which you can see on this plot up here is lower than either asset A or asset B alone. So by combining these two assets, we have lowered the variance for the portfolio to only 1.4%. But if you believe the variance measures risk, then explain to me why the minimum risk portfolio has a probability of loss of 0.99, which is nearly a guaranteed loss, while we could have invested everything in asset B. Let's scroll down to its return distribution. There's also a part of the curve out here that I have cut off in the plot, but the mean is 20% and the standard deviation is 5%. So it has more than 3 times as high standard deviation as the minimum risk portfolio, but it has a probability of loss of practically 0 and a mean return of 20%, while the minimum risk portfolio had a mean of minus 3.1% and a very low standard deviation of 1.4%. Once again, you see it makes absolutely no sense to use variance or the standard deviation as a risk measure for investing. And it is actually even worse than that because Markowitz method tries to maximize the mean and minimize the variance at the same time. So it will try to find an optimal compromise between these two conflicting measures. And that means it can push up the portfolio weight for assets that have negative returns, or at least lower than the other assets, if only it can help lower the variance of the overall portfolio. And that is what I call the double whammy of risk taking. Because if you have estimation errors in the mean and the correlation or the covariance matrix, then Markowitz method can push up the portfolio weights for losing assets that are highly correlated. Now let's move to the next section, which debunks another common myth from academia, and I call this naive forecasting. When you read academic papers on portfolio optimization, typically what they do is they make a naive forecast of what the future returns are going to be. So they will say that the mean and standard deviation for the past returns let's say the last 30 days or 60 days or 12 months or whatever, that those are just going to continue in the future. And then they use that as an input for their portfolio optimization method. That is a very bad idea. First of all, because naive forecasting doesn't work. Secondly, because you are then conflating testing of your forecasting model with testing of your portfolio method. And I will go into more detail in that a little later. But let's look at why naive forecasting doesn't work. So these plots show the mean daily return for different window lengths. So these are basically called moving averages, where we consider 20 days for the blue lines, 60 days for the yellow lines, and 250 days for the green lines. And that's roughly how many trading days there are in 1 year. And the top plot is for the Apple stock, and the second one is for one called Bed Bath & Beyond, which has had some problems in the recent years with falling profits and so on. So its stock dropped dramatically and it was a lot more volatile. And at the bottom, we have one for Foot Locker. What you see in all of these examples is that for the short window lengths, when we are taking moving averages for only 20 days, the lines are very erratic. They get smoother as we increase the window length, but they are never really stable, so you can't really use them to predict the future. And this is what I call naive forecasting. And the next page has examples for the standard deviation, and we see the same problem that when we have short window lengths, the lines are very erratic, and they do get smoother as we increase the window length. Even for a window length of 250 days or 1 trading year, you see we have a high value here, and then suddenly it drops much lower. So you can't use this value up here to predict what is going to happen in the next year for the standard deviation. And down here for the Bed Bath & Beyond stock, you have a fairly low value down here, and then suddenly it increases in the future. So again, the naive forecasts don't work for the standard deviation either. And finally, we show it for the correlations. So again, for short window length, it is very erratic. Here we have the correlation between Apple and Bed Bath & Beyond. And the next plot shows the correlations between the Apple and Foot Locker stocks. Again, as we increase the window length, it gets smoother. But just using the past values as a forecasting for the future is a very naive way of doing it. So the next section briefly discusses what I call conditional forecasting, because we need what is called a conditional probability distribution to forecast the future. And I show an example here for the Apple stock, where we take on the x-axis, we have the price to sales ratio, and on the y-axis, we have the future stock returns. And in the top plot, we have the average annualized return for 2 to 3 year investment periods. So we basically go through the entire data set, and I believe it goes from 2007 to 2021, something like that. And for each day, we take the price to sales ratio for that day, and then we calculate the future 2 to 3 year annualized returns, take the average of those, and then we have one dot in this scatter plot here, and we do that for all days. And furthermore, we convert the 2 to 3 year average annualized returns into the daily returns. But what you see here is a clear relation, so that when the price to sales ratio is lower, the future return on the stock is higher if you hold the stock for 2 to 3 year investment periods. And conversely, if the price to sales ratio is high, then the future return on the stock is low. Again, if your holding period is between 2 and 3 years. And we see that there is a strong relation overall, but in between, when the price to sales ratio is in this range here, there is a lot of noise in the plot. I have written an entire paper and made a previous video lecture on this called long-term stock forecasting. So I won't go into detail with this here. What I want to show here is that if we compare this when we take 2 to 3 year investment periods versus only daily returns, there is a clear relation in the long-term returns, and there's absolutely no relation in the short-term returns. And if we combine these two into one plot, we see that the 2 to 3 year returns are still in the data, but it is completely dominated and hidden by the daily return. If you are trying to do daily stock forecasting, you are trying to predict the green dots. But what we see here is that the daily returns are completely random, and they completely dominate an otherwise pretty strong signal that we had up here. This data here is the same as the blue data here. And here we have an example for the Foot Locker stock. And again, we see the same principle. Lower price to sales ratios means higher returns in the future and vice versa. And again, we have that the green dots completely dominate the blue dots, but it is actually quite reliable. And when you're out here in the extremes, when you convert this into annualized returns, these are actually good returns of probably something like 20 or 30% when it's converted into an annualized rate. And over here, when the price to sales ratio is very high, the annualized returns would be negative, maybe something like minus 10 or 20%. But again, I have written an entire paper and made another video lecture on exactly this topic, so I won't go into detail with this here. I will just give another quick example, which is for the Bed Bath & Beyond stock. And here it is not a clear relation between the price to sales ratio and the future 2-3 year returns on the stock. So it doesn't always work. But again, my paper and the other video lecture explains exactly when it works and when it doesn't work. My point with this example in this paper is that you need to have a conditional probability distribution. You need to have a predictive variable that you can input into some mathematical model so it outputs a likely return distribution. You cannot just use the naive forecast by taking the past, let's say 12 months returns and assume they will continue into the future. You need to have a conditional probability distribution. That's my point with this section here. And also showing that if you want to predict daily returns, you're basically trying to predict what other people and other computers are doing in the market, and they're trying to predict what you're gonna do, and it's really a foolish game. If you can predict the returns over 2, 3, 5, 10-year periods, you're gonna do extremely well. Okay, so the next section of the paper is about random walks, because academia often believes that stock prices and other financial assets move as complete random walks, so-called independent and identically distributed random variables. And I wanted to debunk that myth in this section here. So this plot here shows what I call the random walks and the semi-random walks. The completely random walks that they are using in academia is where we have taken the data for 14 years of the Apple stock, we have taken its mean daily return and its standard deviation, and then we have used this in a very simple random model that draws random numbers every day, using these return distributions. The x-axis here is for the dates, and the red line shows the actual share price for the Apple stock, normalized to begin at 1, and the y-axis is logarithmically scaled, and the blue lines here are for the completely random walks, and you see that they are several orders of magnitude higher or lower than the actual share price, which means that the random walks become completely absurd. We're talking about that you could buy the Apple stock for practically nothing, or that it would be insanely expensive, like more money than there is in the universe or something like that. It is much better to use what I call a semi-random walk, where in the short term the stock prices are random, but every single day they adapt the mean of the return distribution to what the intrinsic value of the stock is going to be in the future. And this example cheats. So the future stock value in 1 year divided by the random stock price right now, and that is the mean in the return distribution. And those random trials are shown as the green lines here, and you will see they are random, but they are much closer to the actual stock prices than the blue lines. In reality, you wouldn't know what the intrinsic value of the stock is, of course. That is the whole game. You're trying to find out what is a fair value 2, 3, 5 years for this stock. We don't want to predict day-to-day stock returns. We want to predict more mid-term or long-term stock returns. But we know that in the short term, it is as if the stock prices are almost completely random. Anyway, I just wanted to give some examples that another one of the common beliefs in academia really doesn't make much sense, that stocks are complete random walks with so-called IID return distributions. So now we get to the main content of this paper, which is the new portfolio method. And it is divided into 2 separate parts. First, we have what I call the filtering method, and then we have the diversification method next. The filtering method is almost trivial. We have 2 kinds in this paper. One I call the threshold filter, and one I call the adaptive filter. The threshold filter basically only lets assets into the portfolio if your conditional probability distribution for the future returns says that the mean return is going to be higher than, for example, 10%. Then we let that asset into our portfolio, otherwise not. Why would you allow assets into your portfolio if you have estimated that the returns are going to be negative? That would be completely moronic. But Markowitz mean-variance portfolio method that won the Nobel Prize can do just that if the asset has a negative correlation with other assets in the portfolio, because that would lower the overall portfolio's variance, as we saw in one of the previous counterexamples why variance is a very bad risk measure for investing. We need to separate these two parts. So first we have the filtering. We only allow assets into the portfolio if they have a sufficiently high estimated return. And the threshold filter is very simple. Either an asset is included in the portfolio or it's not included. And then the weights for all of the assets that are included in the portfolio are set to the same value. So as long as they have sufficiently high returns, they are just equal weighted. Obviously, that doesn't make so much sense either, because if we have an asset that we have estimated to have, let's say, 12% return, and we have another asset that we have estimated to have 30% return, if we have the same confidence in our estimates, we should put more of our portfolio into the one that has a higher return. One method of doing this is called the Kelly criterion, which was used by a mathematics professor named Ed Thorpe, who made the first real hedge fund. But the problem is that it is difficult to calculate for an entire portfolio, and it is also very sensitive to estimation errors, so it can put a massive part of your portfolio into a single asset if that is estimated to have a very high return. So if you made an error in that estimate, you can put a very large part of your portfolio into the wrong assets. What we're going to do instead is to make what I call an adaptive filter, and it's almost trivial. We have a minimum for the asset's mean return, and below this minimum, the portfolio weight is 0, so the asset would need a higher future return than this minimum threshold here. But then we increase the portfolio weight linearly until it reaches some maximum point where we clip the portfolio weight to some maximum value. And the mathematical formula looks like this. So now we get to the second part of the new portfolio method, and this is the really original part. As far as I know, this is a completely new method of diversifying a portfolio. And the section is long, but the method is actually fairly simple. The only thing that is really complicated here is the convergence proof, but we'll get to that in a moment. So I had the original idea during the coronavirus panic in early 2020, where I saw some assets were moving up or down 10-20% a day, and a lot of them were moving together and others did not. So I wanted to have a simple method to avoid that all of the portfolio were moving in synchronization all the time. And the basic idea can be demonstrated with a simple example. We define something I call the full exposure, which measures how much the portfolio is exposed to an asset, both through its direct investment in that asset, but also indirectly through that asset's correlation with other assets that we have invested in. So let's say we have a very simple portfolio with only two assets, asset A and asset B, and the weight of asset A is 9% and the weight of asset B is 12%. So for example, we have used the filtering method from before to determine that we want to invest 9% of our portfolio in asset A and 12% of our portfolio in asset B. Furthermore, let's say that the correlation between these two assets, so their tendency to move up or down in price together, is 0.5. So they do have a fairly strong tendency to move together, but it's not a perfect correlation. Sometimes one goes up while the other asset goes down, but a lot of the time they do kind of tend to move together. So my first intuitive definition of the portfolio's full exposure to asset A is the portfolio weight of asset A plus the correlation coefficient between asset A and B multiplied by the portfolio weight for asset B. So that would be, in this case, 9% plus a half multiplied by 12%, and this equals 15%. So we thought that we had only invested 9% in asset A, but because it is correlated with asset B, which we have invested 12% of the portfolio in, the full exposure of asset A is actually 15%, which is significantly more than the 9% we thought we had invested in asset A. We calculate the same for asset B. So the full exposure of asset B is its direct investment, the weight for asset B, plus the correlation with asset A times the weight for asset A. And this gives a full exposure of 16.5%, where we thought we had only invested 12% of the portfolio in asset B. Now what we want to find are new portfolio weights, which I have marked with a star or an asterisk, I think they call it in English, so that when we use that new portfolio instead in the formulas for the full exposure, so we have the new portfolio weight for asset A plus the correlation between asset A and B multiplied by the new portfolio weight for asset B, then we want that to equal the originally desired portfolio weight for asset A, and similarly for asset B. So we have these two equations here that we need to find the solutions for, and it turns out that the adjusted portfolio weight for asset A should only be 4%, and the adjusted portfolio weight for asset B should be 10%. And if we insert these numbers here in these formulas here, then we get the full exposure to equal 9 and 12% respectively for asset A and B, which equal the originally desired portfolio weights. This is fairly simple to calculate for a portfolio with only 2 assets. It gets a lot more complicated when we have more assets. And another thing is that this definition of the full exposure, although it is intuitive, it is not completely correct. Before we give a proper definition of the full exposure, let's first consider when we need to adjust the portfolio weights. I have made a table like this where we consider combinations of positive and negative portfolio weights. These are also called long and short positions, and positive and negative correlations between them. And these are all the combinations. And then in the text, I go through and explain when we should adjust the portfolio weights and when we shouldn't. What we want in the portfolio is basically the assets to move in opposite direction of each other. So we want negative correlations. And whenever we have negative correlations, we do not want to adjust the portfolio weights. But this gets complicated when we can also have negative portfolio weights, because in some cases, negative correlations become bad, and in other cases, they're good. So it's summarized in the text. I won't go through the arguments in this video here. You can read the text, but it's summarized in this table here, when to adjust the portfolio weights and when not to adjust them, depending on the signs of the portfolio weights and their correlations. And this can be summarized into a very simple formula like this, depending just on the sign of the product of the portfolio weights and the correlation. So let me just explain the concept of the full exposure using this diagram here. First, we have the original portfolio weight here for some asset I, and then we have the full exposure is something more. It is the exposure of the portfolio to asset I through correlation with other assets in the portfolio. And conceptually, what we want is we want to adjust not only the weight for asset I, but also all the other weights in the portfolio, so that the full exposure of each of those assets become equal to the originally desired portfolio weight. So the original desired portfolio weight here should equal the full exposure once we have adjusted all of the portfolio weights. The first definition I made of the full exposure was the basic example I gave you before. And I spent some time trying to figure out the cases where it didn't work very well. And I came up with these basic rules or criteria that should be satisfied for the full exposure. For example, if the weight for an asset equals 0, then the full exposure for that asset should also equal 0. If the weights for all of the other assets in the portfolio or their correlations to asset I are 0, that means that the asset I doesn't have any correlations with any other assets in the portfolio, so the full exposure should just equal the originally desired portfolio weight. What condition 3 and 4 basically just means is that the magnitude of the full exposure should be greater than the originally desired portfolio weight. If we go back to the diagram, it means that we always have a situation like this, that the full exposure is greater than the originally desired portfolio weight. And this means that we have to decrease all of the portfolio weights in order to get the full exposure equal to the original portfolio weight. This is a key feature that makes it a very different portfolio method compared to, for example, Markowitz method, because this means that our method will only decrease the portfolio weights. It will not increase the portfolio weights just because some assets have negative correlations. It will only decrease the portfolio weights, and that means the worst that can happen is that the portfolio method will move too much of the portfolio into cash. There are a few more criteria for the definition of the full exposure, and those are discussed in the convergence proof. I experimented with different definitions, and the one I found to work best was this one here. I haven't made a comparison between different definitions of the full exposure in this paper, because I could easily add another 20, 30, 50 pages to make very complete testing. I'm not gonna write such a paper, so I encourage you to do it, and you can basically do it by just modifying the computer code that I have provided, and I will get to that later in this video. But the definition of the full exposure that I use here is basically we take the sign of the original portfolio weight and we multiply it with the square root of the sum between the portfolio weight for the asset I multiplied with the portfolio weight for some other asset J and the squared correlation between them, and then whether or not this is a bad correlation or a good correlation. We're taking the square of the correlation because we're taking the square root out here, but again, this is something you can test which one works better in practice. And you should also try and check that this definition of the full exposure satisfies the 4 criteria that I showed you just before. Now, the classic way of optimizing this problem is to define the mean squared error, and we want this to go to 0. And there are many different optimization methods for solving this problem, and I have implemented it in the research computer code, so you can try that if you want. It works, but it is very, very slow, and we can make much better and much faster algorithms if we tailor them to this specific problem. The first algorithm we make is basically we calculate the inverse of the full exposure, and we find out that this is basically just a second-degree polynomial, and there is a well-known solution for that. The problem is that once we have solved that for one portfolio weight, because they are all interconnected through the correlation with each other, it is like they are all pulling the full exposure of each other. So we calculate the optimal portfolio weight for one asset, but that will automatically pull all the other adjusted portfolio weights slightly away from their optimal solutions. So we have to do this in iterations, and in each iteration we get a lot closer to the optimal solution, but in each iteration they pull each other slightly away, but it gets much better, much better, much better in each iteration. And so the algorithm actually converges to the optimal solution very, very quickly. And this is also implemented in the research code that I will show you later. The only problem with this is that it is made specifically for this definition of the full exposure. So if you want to experiment with other definitions of the full exposure, you need to mathematically derive the inverse again. So instead I came up with a general algorithm. Actually, this is the reverse order. I came up with the general algorithm first, and much later I came up with the inverse algorithm. But it doesn't matter. The way I thought about this problem was a bit like how you optimize an artificial neural network, if you're familiar with that, using something called gradient descent. Now, I don't use gradient descent here, but I thought about it. Okay, we know what would be a better solution to this problem. Let's move a step in that direction. That's how I thought about it. And the algorithm is like this. It is fairly simple, and it has this step size in it so that I thought if it didn't converge, then you could lower the step size so it would probably be more likely to converge. But it turns out we can actually set this step size to 1, and we can prove that it still converges. So this brings us to the simpler algorithm for adjusting the portfolio weights so that their full exposure equals the originally desired portfolio weights. This equation here is basically just when I set the step size to 1 and go through all of the steps in the previous algorithm, I derive this equation down here, and this shows how to update the portfolio weights in each iteration. And it's very simple. It just takes the portfolio weight for asset I for the previous iteration K, and it multiplies that with the originally desired portfolio weight divided by the full exposure for asset I and the previous iteration K, using all of those adjusted portfolio weights from the previous iteration. And if these two over here are equal, so the full exposure equals the originally desired weight, then this fraction here is 1, which means the algorithm has converged. So that is what we're trying to approach. And the algorithm is very simple. First, we initialize the adjusted new weights by setting them to the originally desired portfolio weights. We will see some examples later that we can actually initialize to completely crazy values and the algorithm still works, it still converges. It only needs one iteration to fix those completely crazy weights. But then we have the number of iterations where we just calculate the full exposure for the adjusted weights. And then we update the portfolio weights using this formula up here. And then we assess or measure whether the full exposure is already close enough to the originally desired weights. And then we break out of the algorithm. And typically, for a sufficiently precise solution, we only need something like 7 iterations of this algorithm. And that is independent of the number of assets in the portfolio. It only depends on how precise a solution we want and how far away the full exposure is from the initial weights. But typically, for acceptable values, you only need something like 7 iterations of this algorithm. So it's very, very quick. And the time complexity is quadratic because if we have n assets, then it takes n computations to calculate the full exposure for each asset, and we have to calculate that for each asset, so that is n times n. So it's quadratic time complexity. And for a portfolio of 1,000 assets, it can do it in just a few milliseconds. Then I use the same basic example as I used in the beginning of this section, where we only have 2 assets, A and B, and the originally desired portfolio weights were 9 and 12% respectively. And then I use the algorithm that you just saw and calculate it manually by hand, step by step, so you can see what happens in the algorithm and how it gradually and very rapidly converges to the optimal solution. And I recommend you go through these steps yourself so you understand how the algorithm works. I also give a lot more examples where I don't go through all the calculations, but you can see the intermediate steps of the algorithm when it is gradually improving the weights of the portfolio to make the full exposure closer to the originally desired weights. For example, let's say that the weight of the first asset is minus 9% and the originally desired weight of the second asset is plus 12%, and the correlation between them is minus 0.5. And you see the steps of the algorithm here, where already in the second iteration, the full exposure is very close to the desired value of minus 9.0. And after a few more iterations, it's very close. And the same for the second asset. One iteration, it's almost 12%, and a few more, it's practically 12%. We also see the mean squared error between the full exposure using the adjusted portfolio weights and the originally desired portfolio weights. And as you can see, the mean squared error decreases by several orders of magnitude in each of the iterations. So the diversification algorithm is extremely fast when we only have 2 assets. And I have several more examples like this that you can go through yourself. Now we get to the convergence proof for the algorithm, and I'm not gonna go through this in this video here because it would take quite a while. I will just speak about what the main idea is. I worked on this for about 1 month. The proof that I give here, I had that fairly quickly, but I'm not completely happy with it. It is a bit too hand-wavy, so I tried for another several weeks to make a better convergence proof, but my mathematical skills are fairly limited. And it has been more than 20 years since I was forced to study mathematics at university when I studied computer science. So if you are capable of making a better convergence proof, it would be a great contribution to this work. The basic idea is that I consider the bounds for the full exposure when we are updating the portfolio weights using the simple equation and the simple algorithm I showed you a moment ago. And then I show it is bounded like this formula down here. And I won't go into what all of this means, but I make a small diagram of it here where we have the full exposure for the updated portfolio weights is in this gray box here somewhere. So between this boundary here and this boundary here, and it is centered around this value up here, which is a point that is roughly between the originally desired portfolio weight and the full exposure from the previous iteration of the algorithm. So it gets much closer on each iteration, and that's the basic idea. But again, it would be great if somebody is more mathematically skilled than me, who could make a better convergence proof, and possibly one that could be more general, that does not rely on the exact mathematical definition of the full exposure. And I give a few ideas in the text that you might pursue, something like Banach, fixed point theorem, and things like that. So the next section argues that if we initialize the adjusted portfolio weights using the originally desired portfolio weights, then the algorithm is most likely going to converge very quickly. But even if we use completely crazy values for the initial portfolio weights, then the algorithm only needs one iteration to bring that back into a normal range again. And the paper gives several examples of that. We have one here where the initial weight for asset 1 is 100,000%, and the initial weight for asset 2 is 0.01%. So their full exposures are completely crazy, but already after one iteration, the full exposure gets brought into a more normal range of 11% and 12% respectively, and in just a few more iterations, the algorithm converges to the optimal values. So the full exposure is very close to the originally desired portfolio weights of 8% and 12% respectively. I already explained about the time complexity before, but let's look at this plot here, which shows the actual time usage for the diversification algorithm for different portfolio sizes. And it works by generating a lot of random portfolio weights and random correlation matrices. And then it calculates the mean time usage for the diversification algorithm on that. And you can check that this is a quadratic rise in time usage with increasing portfolio sizes. And for example, for the biggest portfolio size I tried of 30,000 assets, it took 16 seconds on average to calculate the optimal portfolio weights using the simple diversification algorithm that you just saw. A portfolio with 1,000 assets only takes 20 milliseconds on my computer using my Python implementation. And if you only have 100 assets, it takes a tiny fraction of a second, and it is so fast that you can easily use this diversification algorithm for backtesting, for high-frequency trading, or a stockbroker that has trading robots for their clients can also use this because it's extremely fast. And now we get to the testing with real-world data, and we use a dataset with almost 950 American stocks between the years 2007 and 2021. And we will test different portfolio methods against each other. We have a very simple buy and hold, which buys the stocks at the very beginning of the data period and holds them until the end, and it doesn't do any rebalancing at all. Then we have a simple rebalancing, which rebalances the portfolio every day to equal stock weights. Then we have what I call rebalanced plus, which is basically the rebalancing with equal daily stock weights plus the diversification method, and that uses the actual future 10-day stock correlations as input to the algorithm. And I will explain why we do that in a moment. Then we have the simple threshold method, which only lets stocks into the portfolio if their future 2 to 3 year average annualized returns exceed 10%. And again, we use the actual future stock returns that I will explain why in a moment. And all of those stock weights are equal, but they're only allowed to be max 10% of the portfolio. So if there's only 3 stocks that satisfy this criterion, they're only allowed to be a total of 30% of the portfolio, and the remaining 70% of the portfolio is kept in cash with 0 return. And this is also rebalanced every single day according to this threshold. Then we have the adaptive portfolio, which increases the portfolio weight if the future 2 to 3 year annualized returns are higher. Then they get a bigger place in the portfolio. And once again, these are limited to max 10% of the portfolio. So if there's not enough stocks available with high enough future returns, then a significant part of the portfolio, or maybe all of it, may be held in cash, which earns 0% returns. And finally, we have the adaptive plus portfolio, which is basically just the adaptive portfolio method with the diversification method as well. And that again uses the actual future 10-day stock correlations as the input to the algorithm. This is what I call omniscient testing. In academia, they usually use the word ex post testing, but I can never remember the difference between ex post and ex ante. So I prefer to call it omniscient, which means all-knowing. And we do omniscient testing first, where we use the actual future stock returns and the actual future stock correlations to test if the portfolio methods work if we use correct input. Later on in the paper, we do robustness testing, where we add a lot of noise to it. The reason we do it like this is because when you test a portfolio method, you basically have three components. First, you have to forecast the financial data, the future stock returns and their correlations. Then you have to use your portfolio method to calculate the portfolio weights. And then you have to buy and sell assets to match those portfolio weights that you have calculated. The problem in a lot of the research papers in academia is that they conflate all three parts. As I explained before, they like to use the naive forecasting, so they take the mean return of the stocks for the past, let's say, 3 months, and their correlations for the last 3 months, and then they assume that those are going to be good estimates for the next 3 months or whatever, but they are conflating the forecasting method with the portfolio method. We need to separate these, and that is why we're using omniscient testing, so that we are using the actual future stock returns and the actual future stock correlations to see if the portfolio method does what it is supposed to do when the input is correct. That's a proper way to do a scientific testing of a portfolio method. And we have the flowchart for it here. So first we calculate the actual future 2 to 3 year annualized returns of the stocks. And then we calculate the actual future 10-day stock correlations. And in the omniscient testing, we do not add noise to this, but we do that in the robustness testing, and we will get back to that. Then we take the future stock returns and send that through the filtering method. And this could be either the threshold or the adaptive method. And this outputs portfolio weights that we send into the diversification method along with the future stock correlations. And this adjusts or lowers all of those portfolio weights to maximize the diversification of the portfolio. And the resulting portfolio weights can actually sum to more than one, so they have to be normalized. And finally, we use those portfolio weights to decide which assets we should buy and sell on a daily basis. And then the test procedure is that we have different choices of portfolio size, 5, 10, 30, 50, 100, and so on. And for each of those, we will run 128 random trials. For example, first we take 5 random stocks. Then we run all of the different portfolio methods. We calculate various performance statistics and save those for later. Then we take another random 5 stocks, do the same. We use all of the different portfolio methods, calculate the performance statistics and save them for later. We take another random 5 stocks and so on and so on. And we do this for all the different choices of portfolio size, 5, 10, 30, 50, and so on. The reason we use exactly 128 random trials is because we need enough random trials to make the results statistically significant. And a rule of thumb is that you need probably 50 or even 100 random trials, depending on how big the differences are. But the reason I have said 128 random trials is because the code I have written can run in parallel, and I have 8 CPU threads on my computer, and 128 can be divided equally between 8 threads, so it can run much faster. That's the reason why it's 128. If the computer code was not parallel, it would run a lot slower. So the first test, A, is for the full data period, using the omniscient data, so we use the actual future 2 to 3 year stock returns and the actual future 10-day stock correlations. And this is for the entire data set between the years 2007 and 2021. But because we're using these actual future 2 to 3 year average stock returns, the dataset gets shortened, so the endpoint is only in 2018. So all of this text explains what the experiments do and what the results are and so on, What I like to do in this video instead is to show you what the plots look like and what they are, so you can analyze the plots yourself, because there are hundreds of plots in this paper and I can't go through them all in this video. It would be exhausting and you wouldn't listen to it anyway. So the first kind of plot looks like this, and this shows the ratio between two different portfolio methods. So let's focus on the top plot first. We have 128 random trials. Each of those portfolios has 5 randomly selected stocks, as I just explained. And the blue lines show the ratio between the value of the rebalanced portfolio divided by the buy and hold portfolio. And the dashed black line here is for the value 1. So when the blue lines are above 1, it means that the rebalanced portfolios perform better at that point in time than the buy and hold portfolios. And conversely, when their ratio is below 1, it means that the buy and hold portfolios perform better than the rebalanced portfolios. The next plot compares the rebalanced plus portfolios with just the normal rebalanced portfolios. Remember that the plus version is using the diversification algorithm. And as we can see, the rebalanced plus portfolios performed a lot better in this period here, which was the big stock market crash in 2009. But for the rest of the period, it looks like the rebalanced plus portfolios performed worse than the normal rebalanced portfolios. And we also show these plots for the threshold portfolios versus the rebalanced, and the adaptive versus the threshold, and the adaptive plus versus the adaptive. And all of these are for the same portfolio size with only 5 random stocks. And as we can see in all of these cases, as the portfolio method gets more sophisticated, it performs better during the crash in 2009, but then they underperform after that. On the next page, we have the same plots, but now the portfolio size is 30 stocks. And let me again explain what this means. It means that for each random trial, we select 30 random stocks, but only the very basic buy and hold and rebalance portfolios will always be invested in all 30 stocks all the time. As soon as we start using the diversification algorithm or the filtering methods, the threshold and adaptive methods, they may not be invested in all 30 stocks all the time. They could have 100% of the portfolio held in cash sometimes. So what it is that we take a small universe of only 30 random stocks and see how the different portfolio methods perform on that. And then we take another small universe of 30 random stocks and see how the portfolio methods perform on that, and so on. And we do that from 128 random trials. Now we can see that the threshold portfolios perform a lot better all the time than the rebalanced portfolios, but the adaptive and adaptive plus portfolios sometimes perform better and sometimes worse. On the next page, we see these plots for portfolio sizes of 100 stocks. And now the threshold portfolios always perform better than the rebalanced, and the adaptive portfolios always perform better than the threshold, and the adaptive plus almost always perform better than the adaptive. And on the next page, we have these plots for portfolios with 300 stocks. And now we see that the threshold portfolios are always better than the rebalanced, the adaptive are always better than the threshold, and the adaptive plus are always better than the adaptive. So it looks like that these portfolio methods simply need more stocks in the portfolio or in the universe of available stocks for investing, but then they also perform much better. If you look at the y-axis here, you can see that after 14 years of investing, the adaptive plus portfolios are roughly between 4 and 6-7 times better than the adaptive portfolios. So using the diversification algorithm on top of the adaptive filter over a 14-year period, this has resulted in a dramatic increase in performance. Now let's look at the second type of plots that we have. So we have 9 subplots for different portfolio sizes, 5, 10, 30, and so on. All of these plots are for the same performance statistic. In this case, it is for the arithmetic mean of the daily returns. And these are called box plots, so they show the distribution of the arithmetic mean of the daily returns of the 128 trials for different portfolio sizes. You may have to study this plot for a while before fully understanding what it shows, but let's take a few examples. Let's scroll down where we can see what the labels are on both the X and the Y axis. So let's take this subplot here, where the portfolios have 50 stocks. The buy and hold portfolios have an arithmetic mean daily return slightly above 1.0005. Some of them are slightly lower and some of them are slightly higher, but most of them are concentrated around there. The rebalanced portfolios are slightly better, and the rebalanced plus are roughly the same, but some of them are lower, some of them are higher. But the threshold and the adaptive portfolios are significantly better, but the adaptive plus portfolios are slightly worse than those. As we increase the portfolio size to 70, 100, 150, 200, and 300 stocks, you can see the tendency becomes more and more clear that the buy and hold, rebalanced, and rebalanced plus, they don't get any better. But the threshold, adaptive, and adaptive plus become increasingly better. But as we can see from these plots, we need to have a significant amount of stocks in the universe that we are considering. And in the text, I calculate these numbers on the y-axis. I transform them into annualized returns. I cannot remember the exact number, but I think the adaptive plus portfolios is something like an annualized return around 75% or something like that. So these are very high returns. But again, these are cheating. So they are using the correct future 2 to 3 year average annualized returns and the correct future 10-day correlations between the stocks. Later, we will do the robustness testing and see what happens when we add a lot of noise to these future returns and correlations. Okay, the next page has the same kind of plot, but this time it is for the geometric mean of the daily returns of the portfolios. These are actually almost exactly the same as the arithmetic mean, so this plot has been omitted for all the other tests in the paper. The next page has it for the standard deviation of the daily returns. And for small portfolio sizes with only 5 or 10 stocks, you can see that the buy and hold and rebalanced portfolios have a much higher standard deviation than the rebalanced plus, threshold, adaptive, and adaptive plus. The reason is simply that these methods hold a lot of their portfolios in cash when the portfolio universe only is very small, like 5 or 10 stocks. As we can see, when the universe of available stocks grows to 150, 200, or 300, the standard deviations are roughly the same for most of them, except for Rebalance Plus, which is much lower than the rest of them. The next page shows the Sharpe ratio. So this is the mean daily return divided by the standard deviation. And as we can see in all of these plots, regardless of portfolio size, the tendency is the same, that the Sharpe ratio increases more and more and more for the more sophisticated portfolios. The next page shows the daily average cash position for the different portfolio methods. And the first two here are the buy and hold and rebalanced, and these are always 0 because these are always fully invested. But the Rebalance Plus, the threshold, the adaptive, and the adaptive plus, for small portfolio sizes where only a small number of stocks are available for investment, these portfolio methods will hold a lot of cash. And even if we go up to portfolio sizes of 150, 200, or 300 stocks, the adaptive and adaptive plus methods can also still hold a significant amount of cash because they are not fully invested all the time. And this indicates that these portfolio methods could actually benefit from even larger portfolio sizes, maybe 400 or 500 stocks. The next page shows the months with losses for the different portfolio methods. And as we can see, for all of these subplots, the tendency is the same, that the buy and hold and rebalanced portfolios have roughly 35% of all months have losses. The rebalanced plus portfolios are slightly better, but especially the threshold, adaptive, and adaptive plus are much better. And the best ones are the adaptive plus, where about 15% of the months result in losses. The next page shows the max drawdown. So this measures the maximum crash for the different portfolio methods. And remember that for small portfolio sizes, some of these portfolio methods hold a lot of cash. So let us instead compare the larger portfolio sizes. And we can see that the buy and hold and rebalance portfolios have roughly the same max drawdowns. But the threshold, adaptive, and adaptive plus are usually slightly better than those others. But remember that the threshold, adaptive, and adaptive plus methods use the future 2 to 3 year average annualized returns. They are completely blind to what happens in between. So if a stock market crash happens in 6 or 12 months, they cannot see it and they will invest anyway. And that is why their max drawdowns are not significantly better than for the buy and hold and rebalanced portfolios. The next page shows what I call the max pull-up, and I don't know if this is my invention or not, but this is what I call it. And this is the opposite of the max drawdown. This measures the pull-up from the bottom of a stock market crash to the top within maximum 1 year. Again, for smaller portfolio sizes, some of these portfolio methods hold a lot of cash, so let us consider the larger portfolio sizes. And the tendencies are the same, already starting from portfolios with 70 stocks going up to portfolios with 300 stocks. For example, here for 150 stocks, the rebalanced portfolios perform significantly better than the buy and hold. The rebalanced plus are about the same as the rebalanced. The threshold are significantly better. The adaptive portfolios are much better, and the adaptive plus portfolios are really good. Most of these range between roughly 400 and more than 500% gains, when the buy and hold is only probably around 100%. So if you're using the actual future 2 to 3 year stock returns and the actual future 10-day stock correlations with the adaptive plus portfolio method, then you can do a lot better coming out of a stock market crash. Now, because the adaptive plus method performed so well going out of a stock market crash, and there was really only one huge stock market crash in this period between 2007 and 2018, and that was the crash in 2009, I wanted to see if all of the great performance for the adaptive plus portfolio is only because of that stock market crash and because the adaptive plus method performed so well coming out of that crash. What about more normal times? Does it still perform well? So in the next two sections, test B and test C, I have split the data set. So in test B, we consider the data until the year 2010. And the next one, test C, we consider the data from 2010. So let us go down to the plot for the max pull-up for the period between 2007 and 2010. And we have that here. And we can see that for this period, we had the massive max pull-up coming out of the stock market crash in 2009. So the next section with test C considers the data from 2010 onwards. And now you know how to look at all of these plots, and to save some time, I'm gonna jump directly to the plot for the max pull-up, and you can analyze the rest of the plots yourself. So we have that here, and if we scroll down to the large portfolio sizes, we see the exact same tendency as before. It is really only the scale on the y-axis that is different, because there were no big stock market crashes between 2010 and 2018. So we can see that in more normal times, the threshold, adaptive, and especially the adaptive plus portfolios perform much better than the buy and hold and simple rebalancing. So let's go to the next section, and this starts the robustness testing. So we are still using the actual future 2 to 3 year average annualized stock returns and the actual future 10-day stock correlations. But in this test D, we add a lot of heavy noise to the future 2 to 3 year stock returns. I will only go through this section very quickly to show you a few of the performance statistics. So here we have the arithmetic mean daily return. And if we scroll down for the larger portfolio sizes, we have the same tendencies for all of these plots. So that even when we add heavy noise to the future stock returns, the threshold, adaptive, and adaptive plus portfolio methods still work really well compared to the simple buy and hold and rebalanced. And this is really heavy noise that I'm adding. Some of the stock returns that are like minus 30 suddenly become plus 50 and vice versa. And another interesting thing is that the daily average cash position for these portfolio methods actually becomes lower when we add noise to the future stock returns. Already for portfolio sizes with 70 stocks, all of the portfolio methods are mostly fully invested. They have very little cash. So let's go to the next section with test E. So this still uses the actual future 2-3 year average stock returns without any noise, but now the correlations have a lot of noise. We are still using the rebalanced adaptive and adaptive plus portfolio methods from before, but now we use the adaptive plus portfolio method with various different kinds of noise in the correlation matrix. In one kind, we add heavy noise, and another kind uses pure noise in the correlation matrix, so there's no actual correlation signal whatsoever. Another one uses naive forecasting, so it takes the previous 10-day period, calculates the stock correlations for those, and uses that as an estimate for the future stock correlations. Another one uses the stock correlations for the full data period between 2007 and 2018. Another one sets all the stock correlations to equal 0.1, except for the diagonal in the correlation matrix, which is always 1. And finally, we take the actual future 10-day stock correlations, but we invert them. So for example, a positive correlation of 0.5 becomes a negative correlation of minus 0.5. So they are completely the opposite of what they should be. I'm going to go through these plots very quickly as well, and you can study them in more detail yourself. So here we have for the arithmetic mean daily return. And if we scroll down for the larger portfolio sizes, and so we can also see the names of the different portfolio methods, we see that all of these adaptive plus variants, so they are using the diversification algorithm with various kinds of noise and malformed correlation matrices. And we can see that they have roughly the same arithmetic mean daily return. So even with very heavy noise in the correlation matrix, or a correlation matrix that is completely malformed, it may be the inverse of what it actually should be, it really doesn't harm the portfolio performance. In a lot of these cases, it still actually helps the portfolio performance, but it never gets worse than the adaptive portfolios which don't use the diversification algorithm. So this seems to confirm that our diversification method works as intended, that it will only lower the portfolio weights, and the worst that can happen is that it moves too much into cash. But remember, this test here used the actual future 2 to 3 year average annualized returns for the stocks, so the stock returns were still cheating, and maybe that is what the diversification method implicitly exploits, and that is why it still performs so well. So let's go to the next test F, which uses heavy noise in both the future stock returns and the correlations. Let us jump right to the plots for the arithmetic mean daily return, and we scroll down to the large portfolio sizes, and we can see the same tendency as before, that the adaptive plus portfolios with various kinds of noise in the correlation matrix never really perform worse than the adaptive portfolio methods, which don't use the diversification algorithm at all. So the diversification algorithm is extremely robust to noise. And again, I encourage you to study the other performance statistics by yourself. So now let's go to the final test, which is about parameter tuning. Because as you saw in all of these performance statistics, the threshold and adaptive portfolio methods didn't work very well for small portfolio sizes because they would place too much of the portfolio into cash. The diversification algorithm does not have any parameters that we can adjust, but the filtering method does. And I had set those parameters to what I thought was reasonable, but that also meant that they would place a lot of the portfolios into cash when there were few stocks available for investing. So what we do in this section is we want to tune the parameters of the adaptive filter so it works better for portfolios with only 30 stocks. This is a simplified computation flowchart of how we tune those parameters. The central part is this part down here, which is called the NSGA2 optimizer. This is a so-called multi-objective optimizer, which makes various proposals for the parameters for the adaptive filter, and then we run simulations of random portfolios with 30 random stocks each, and we calculate the rebalanced portfolios and the adaptive portfolios using these parameters that were given by the optimizer down here, and we feed those performance statistics back into the optimizer, and then it makes another guess for the parameters for the adaptive portfolio method, and we continue this loop until we have found a good solution. And then we get what is called a Pareto front, which is very similar in concept to what the mean variance optimization is about, but it's also very different because what we have here are different dots. These are different parameter choices for the adaptive portfolio method. And these are the optimal compromises between when the adaptive method performs better than the rebalance method and the max drawdown for the adaptive portfolios themselves. I have taken 3 of these parameter sets, call them test G1, G2, and G3, and these are optimal compromises. So the parameters for G1 have the best max drawdown. The max drawdown is 0, and that is because these parameters don't invest in anything. But that also means that it underperforms the ordinary rebalanced portfolios. We can take the best compromise between these two, where the average daily return is roughly the same for the adaptive portfolios and the rebalanced portfolios, and the best parameters that were found for the adaptive portfolios gave a max drawdown of only something like minus 28%. So roughly the same mean daily return as the rebalanced portfolios, but a max drawdown of only minus 28%. And we don't show that here. The max drawdown for the rebalanced portfolios with 30 stocks, that was like minus 50 or minus 55%, something like that. So this is actually a much better performance. And finally, we have the last parameters out here. These are the optimal parameters for the adaptive portfolio method that maximizes its performance relative to the rebalanced portfolios. And let's go down and look at the performance statistics for those parameters. So the parameters, you can see them here, and these were very, very different from the ones that I have set manually for all the other experiments in this paper. I think I had set this to 10%, and this one to 30%, and this one to 5 or 10%. So it's very different what it does when it wants to maximize the performance of the adaptive portfolios compared to the rebalanced portfolios. So let's take a look at the performance statistics. Here we have the arithmetic mean daily return, and you can see that the adaptive portfolios, which we have here, performed much better than the rebalanced portfolios that we had here. It also had a much higher standard deviation, but the Sharpe ratio was still much higher. So now let's look at the computer code. And I have a repository here on GitHub called Finance Ops. And it's a stupid name, but it's basically for my research in finance and investing. And you can run all of this on the internet using Google Colab, so you don't have to download and install anything on your own computer. But here I have it running on my own computer. And this so-called Python notebook generates all of the simulations and plots and statistics and everything else that you saw in the paper. But to make it even easier for everyone else to test and use the new diversification algorithm, I have made this Python package here called InvestOps that you can install and use very easily in your own Python program. I have also made a tutorial so you can easily see how to use the diversification algorithm. And again, you can run all of this in Google Colab. All you need is a Google account. So we have a small example here where we first make some portfolio weights and a correlation matrix. Then we can calculate the full exposure using the mathematical formula that I showed you a while ago from the paper. And then we can call this function here diversify weights. And this is the diversification algorithm that I also showed you a while ago. That function can also take so-called pandas data types as its input. This means that we can name the different assets, for example, using stock tickers like this. So we get a correlation matrix that looks like this, and portfolio weights that look like this. And then the output of the diversification algorithm is also a pandas data type where these different assets have the stock tickers that we used before. This can make it a lot easier to work with, but there is an extra overhead in the algorithm to handle this. So if you want to use it for backtesting or high frequency trading, you really should use the NumPy data types instead. So that was everything, and I will be very curious to see if you use this in your own work or maybe even write some research papers on it. And I wish you good luck. And as it has become very popular to say these days, let's go, Brandon.